times some R, where R is an element of R. And X has to be an element of A, so that means X has to equal A times some other number N, where N is an element of R. And that's as far as we got. So what we want to try to do is we want to try to show that P is not irreducible, so that means that we need to somehow get it so that P is equal to two elements that are not units.
So let me just back up a moment here. So when you say P is not maximal, explain that sort of line with the three sets on it, the ideal generated by P and ideal generated by A and R. What's going on there?
Well, the definition of maximal is that an ideal is maximal if any set that it is contained in, that it's a subset of, has to either be the whole ring, or it has to be that subset itself. So if it's not a maximal ideal, that means that there exists some ideal that it is a subset of that is not equal to the whole ring.
Okay, so we know that there's an ideal that's intermediate between the ideal generated by P and the whole ring. How do we know it has the form bracket A?
Because R is a principal ideal domain.
Because R is a principal ideal domain. So I just wanted to clarify that this is where we're using that assumption. That because R is a principal ideal domain, we can assume that that's the ideal generated by A in the middle. Okay.
And so now because P is a subset of A, then whatever element is in P must be in A.
Okay. So you're saying, let's suppose X belongs to the ideal generated by P. Then X is equal to P times R.
Yeah.
For some element R. Okay.
But then that same element has to equal A times N because it's an element of the ideal generated by A.
Okay. And I think I'm seeing you do what I saw the other group do when they were at this point in the proof.
So I kind of want to say that P times R is equal to A times N.
Well, equality is transitive,
Yeah.
so we can say that.
But now we have to show that P is
Supposed to show the
the product of two non-units.
Does Nick or Jack, do you remember what I told you when you got to this point in the proof? Because you landed in the same spot where you sort of couldn't go forward because you wanted to divide by R,
Yeah.
but we can't divide by R. I think Terry had the notes. She's not here today. So let me just make a suggestion. I want to know what was behind, not a suggestion, a question. I want to know what's behind your choice that you made when you said, let's let X be an element of P, the ideal generated by P. And then you go on to prove something about X, make some statements about X. But it's not really X that we care about. It's P that we care about. So can you make this a more specific statement? I guess I'm trying to say, you're being arbitrary where there's no need to be arbitrary.
Doesn't that necessarily mean that P has to be an A? Wouldn't that be dependent on if R had the identity?
Yeah, I think we need, in fact, I think every principal ideal domain has an identity in it. So let's assume that we have an identity element.
Okay, in that case, then yeah, then we can just say P is an element of A.
How do we know P belongs to the ideal generated by P? Just close that loop for me.
So because R now has an identity, P, the ideal generated by P is equal to P times some R, where R is an element of R. But since the identity is an R, that means we can just do P times 1.
Okay.
And so that's why P is
Got
its
it.
own ideal.
P is equal to P times 1, which is why it belongs to its own ideal. Okay.
So that means then if P is an element of the ideal generated by P, then P has to be an element of the ideal generated by A.
Okay.
Which means that P is equal to A times some N, where N is R.
Okay.
But now the problem is we don't know whether A and N.
I remember
Oh, that's right, because if A is a unit, then it generates the whole
ideal
ideal. The whole ring.
So item 39, theorem number 39, says that units, when they generate an ideal, must generate the entire ring. Okay. So how does that help us here?
So because A is not the entire ring, we can use the contrapositive of exercise 39.
Okay. To conclude,
That A is not a unit.
right. So by hypothesis, you said A was not equal. It was a subset, but it wasn't equal to the entire ring. Thus, A cannot be a unit. So we've ruled one of them out. I think you want A not in our class. Yeah. Okay. So you've ruled out A. What about N? Try to tease that out. What would happen if N were a unit?
Then the ideal generated by N wouldn't be the ideal P would be an element. But that still doesn't necessarily mean anything.
How would N being a unit change the relationship between A and P? If N is a unit, we can divide by it to get what new relationship?
We would get N inverse P equals A.
N inverse P is equal to A. And of what consequence is that?
That would mean that A would be a subset. A would be an element of P.
Okay.
So you get a contradiction.
How do we know it's a contradiction?
Because P is a subset of A, but A is not.
P is what? Say that again.
We know that P is a subset of A, but they aren't equal.
Right. P is a proper subset. That was our assumption, right? That both of those symbols on that line there should be, subset but not equal to. Proper subset. So write that up while I'm writing this up. So if A belongs to the ideal generated by P, then the ideal generated by A is a subset of the ideal generated by P. Contrary to our assumption. So closing the loop, what do we have?
Thus P is not irreducible, hence the original statement holds true.
All right, thus P is not irreducible, completing the proof of the contrapositive. Yep. Very, very nice.